Welcome back. So we're starting a new topic for this lecture. We're starting gravity. This is going to be our last topic. Today's class and Monday's class will cover gravity, and then we will not have a classwork assignment for next Wednesday's class, the last class of the semester. So we'll run a optional Zoom that day, but there won't be any classwork. Your last official homework is due next Monday, and so then after that you'll have an optional homework, and that's going to be due on Monday, May 10th, and then your final exam is also going to be on Respondus, and that's going to be on May 10th as well. So the exam is going to run all day, and so it's going to start at 9 a.m. and then it's going to close at 8 p.m. Alright, so we are starting gravity now. This unit is pretty interesting, especially if you are going to take 202. Gravity and electrostatic forces have a good bit in common. So up until now, we've treated gravity as a constant acceleration. We have found the gravitational force, or the weight of an object, by multiplying the mass of the object times the gravitational acceleration. As long as we're on the Earth's surface, this is a very good approximation, but if we are interested in the gravitational forces between any two objects, or if we're interested in gravitational forces somewhere other than the Earth's surface, we need to understand gravity better to understand their motion. Space, I guess, is the final frontier of this, and if we want to understand the motion of the planets and stars, we need to understand how the gravitational force changes with the mass and distance. So there are four fundamental forces: electromagnetic, gravitational, strong forces, and a weak force. And the gravitational force depends on the mass of the two objects that the force is in between. For the gravitational force to be significant, we need to be talking about at least one very massive object. The gravitational force is extremely weak as compared to these other forces, like electromagnetic forces. But if we are talking about massive objects like planets and stars, then the gravitational forces can become quite large. Also, planetary motion is governed by gravity, and so in the next set of slides, we're going to look at Kepler's law, which help explain the orbits in the solar system. So, gravity is an attractive force. If you have two objects with a mass m1 and mass m2, then they will attract each other. The strength of this force depends on the mass of the two objects, and it depends on their distance, which is labeled r. So if the objects are spherical, like most planets or stars, the distance that matters is the distance from the center of mass of one object to the center of mass of the other object. So if you are calculating the gravitational force between you and the Earth, you would want to know the radius of the Earth, which is about 6,400 kilometers. If you know that distance, then, well, you could convert to meters first, but then once you had meters, then you would have the value for r. If you were flying a plane 10 kilometers up, then your new radius would be 6,410 kilometers, and so you would have to add the height to the radius of the planet. The gravitational force also depends on the mass of the two objects. So if you are interested in the force between the Earth and the Moon, you would need to know the mass of the Earth and the mass of the Moon. It doesn't matter what mass 1 is and what mass 2 is, because the gravitational force on you by the Earth is exactly the same as the gravitational force on the Earth applied by you. This should make sense because of Newton's third law. A force is an interaction between two things, and the direction of the two forces are equal and opposite. The direction of the gravitational force is always attractive, so if you have two masses, one on the left and one on the right, the one on the left will be attracted to the right, and the one on the right will be attracted to the left. The size of the force has to be exactly the same, but opposite in direction. The magnitude of the force is given by Newton's law of gravitation, which is g times mass 1 times mass 2 divided by r squared, where the masses are in kilograms, and the radius is the distance between the center of masses squared. G is the gravitational constant, so it is an uppercase g, and this is not the lowercase g that we've used before, the acceleration due to gravity on Earth. So g, uppercase g, is 6.67 times 10 to the minus 11 Newton meters squared over kilograms squared. The units on g tell you that the unit of mass must be in kilograms, and the unit of distance must be in meters. The force drops off with the square of the distance, so the further apart the two objects are, the smaller the gravitational force. it drops off with the square of the distance. So if you double the distance between two masses, the gravitational force is 4 times smaller. So it would be 1/4 the original force. Okay, so we have a question to do here. So, well, what is the gravitational attraction between a weather satellite that is 36,000 kilometers above the Earth's surface and the Earth? The mass of the Earth is 6 times 10 to the 24 kilograms, and the mass of the satellite is 1,500 kilograms. The radius of the Earth is 64 kilometers, and we're given the value of g as well. Okay, so what usually trips people up in a question like this is getting the right distance. The distance between the center of the Earth and the weather satellite is the sum of the radius of the Earth and the distance from the Earth's surface to the satellite. So 36,000 kilometers from the Earth's surface to the satellite, plus the radius of the Earth, which is 6,400 kilometers. If the distance from the Earth's surface was 0, then r, the distance to the Earth's center, would not be 0. It would be 6,400 kilometers. So we add them together, and we get 42,400 kilometers, and then we convert that to get meters, so that's going to be 4.24 times 10 to the 7th meters. To find the force, we need the masses and the distance. So we already have the distance. So the force is equal to g times mass 1 times mass 2 over r squared. And that is 6.67 times 10 to the minus 11 times 6 times 10 to the 24th kilograms for Earth, 1,500 kilograms for the satellite, and we divide by the 4.24 times 10 to the 7th meters squared that we found earlier. Okay, if we do that, we get a force of about 334 newtons. If this is a 15,000 kilogram satellite that was on the Earth's surface, the force would be about 150,000 newtons. So there's a large change in this gravitational force with distance. Okay, so it's your turn. You have a few questions to do that are pretty similar to this one, but we're looking at a satellite that's around a moon of Saturn. Good luck.